astronomers examined an interstellar visitor and encountered something entirely unexpected: vaporized nickel with no accompanying iron. Harvard astrophysicist Avi Loeb remarked that such a signature is normally associated with industrial processes, not natural cosmic objects. Peer-reviewed studies described the observation as deeply puzzling. Was this simply an unusual case of chemistry, or evidence pointing to something far more extraordinary? As 3I Atlas moved closer to its perihelion, the growing list of anomalies began to divide the scientific community. With every new data point, the boundary between an ordinary comet and a possible artifact became increasingly difficult to define. The central question remained unavoidable: what exactly have we discovered? At the Very Large Telescope, technicians scrutinized raw spectral data from 3I Atlas. Each peak and trough represented atoms stripped free in the vacuum of space. The UVES spectrograph, built for extremely precise measurements, recorded a pattern never before seen from a comet at a heliocentric distance of 3.88 astronomical units. The spectra revealed unmistakable signatures of neutral atomic nickel, NiI, clearly emerging above the background noise. Line after line aligned perfectly with known wavelengths of nickel vapor. Yet iron, normally its constant companion, was absent. No Phi lines appeared above the sensitivity limit of the instrument. For decades, every well-studied comet, whether originating within our solar system or beyond it, had shown iron and nickel together, their signals rising and falling in parallel. In this case, only nickel was present. Data reduction logs confirmed that standard procedures had been followed: bias correction, flat field calibration, and accurate wavelength alignment. The telescope's moving target system kept the spectrograph slit fixed on the coma as the object traversed the outer solar system. After background subtraction and removal of sky emission lines, the nickel features remained intact. To eliminate confusion, researchers cross-checked the signals against multiple atomic databases, including NIST and cruise line lists. The matches were definitive. These were nickel lines, not molecular emissions, not instrumental artifacts. Signal-to-noise ratios were well above the continuum, leaving little doubt. Iron, by contrast, remained undetected, even in spectral regions where the same equipment had easily identified both elements in comets, such as 2I/Borisov. The immediate conclusion was straightforward: at this distance from the Sun, the coma of 3I Atlas contained detectable nickel vapor, but no iron. The data were unambiguous. The deeper question of how nature could separate two elements forged together in stellar interiors was left unanswered. For the moment, the evidence spoke clearly. Nickel was present, iron was not. This alone made the object unlike any interstellar visitor seen before. The European Southern Observatory team described the result as extremely puzzling. In every well-characterized comet observed to date, nickel and iron appear together, never one without the other. Yet in 3I Atlas, only nickel revealed itself, and it did so at a distance from the Sun where neither metal should normally vaporize. The authors emphasize the object's extreme properties, a phrase rarely used in formal literature unless observations genuinely defy expectations. Peer reviewers pressed hard, questioning whether the signal could arise from instrumental effects, misidentified lines, or contamination. The team responded by rechecking the spectra against all available atomic databases. The nickel detections held firm. Iron lines were still absent, even at the noise threshold. Using the same instruments and identical reduction techniques, the researchers had previously detected both metals in other comets. This time, iron was simply not there. When Avi Loeb reviewed the preprint, he highlighted a detail that unsettled many planetary scientists. On Earth, he noted, nickel without iron is essentially unknown outside of industrially refined alloys. In natural settings, these elements form together in stars and remain locked within minerals that are difficult to separate. Loeb did not claim this was proof of technology, but he reframed the debate by asking a pointed question: what natural process could produce such a signature? The paper itself offered no definitive answer. The mystery was now public, and discussion intensified. At 3.88 astronomical units from the Sun, the coma of 3I Atlas displayed only nickel vapor. Iron remained invisible, Chemists and astrophysicists alike began searching for a mechanism that could satisfy both physical and chemical constraints. One proposed explanation involved nickel carbonyl. In industrial chemistry, passing carbon monoxide over finely divided nickel at moderate temperatures produces nickel carbonyl. NiCO4, a highly volatile compound. It can vaporize at temperatures where water ice remains completely solid when exposed to sunlight or ultraviolet radiation. Nickel carbonyl breaks apart, releasing atomic nickel into the surrounding gas. The ESO team suggested that fragile nickel carbon monoxide complexes trapped within the comet's icy nucleus could be liberated as the object warmed. According to this model, beyond about 2.6 astronomical units, surface temperatures become sufficient for nickel carbonyl to sublime, while iron-bearing compounds remain solid. This would naturally explain why nickel appears first. Iron requires higher temperatures and would only become detectable closer to the sun. Laboratory data support the volatility of nickel carbonyl, which boils at around 43 degrees Celsius under Earth conditions and is even easier to release under the low pressures of space. No equivalent iron compound behaves in this way. In this scenario, the chemistry of the comet reflects a carbon monoxide-rich environment in which nickel is carried by a volatile agent, while iron remains locked in more resilient minerals. The model fits the observed sequence, but the anomaly persists. No previously studied comet has displayed this pattern. Even with a plausible natural explanation, the mystery remains unresolved. Long before any official announcement, 3I Atlas had already crossed the fields of view of survey telescopes that did not initially recognize its significance. The Zwicky Transient Facility at Palomar recorded a faint moving object on several nights in June 2025, from the 14th to the 21st, and again near the end of the month. These detections remain buried in archival data, obscured by the vast volume of nightly observations. Uncovering them required persistence. Amateur astronomer Sam Dean, working independently with public survey data, traced the object's faint trail even further back, identifying images from June 5th through the 25th. Each recovery extended the timeline, pushing the record of the object's presence weeks earlier than its official discovery on July 1st. These archival detections were more than curiosities. They allowed astronomers to reconstruct the comet's brightness and activity before its interstellar nature was known. Data from TESS, a spacecraft designed for exoplanet hunting, showed the object already bright and active at 6.4 astronomical units in May. ZTF and ATLAS observations filled in the gaps, revealing a steady, persistent glow. Dean's work, echoed by other amateurs, demonstrated how citizen science can meaningfully contribute to professional research. Every recovered image refined the trajectory and established a baseline for what followed. Before debates over chemistry or speculation began, the evidence had already been quietly accumulating. TESS was never intended to observe comets. Its mission is to monitor stars for tiny dips in brightness caused by transiting planets. Yet in May 2025, it recorded a faint, steady glow moving across its field at 6.4 astronomical units from the Sun, well beyond Jupiter's orbit. Most comets remain dormant at such distances, locked in deep freeze. But 3I Atlas was already active, its coma bright enough to appear in TESS photometry. The light curve showed a persistent rise rather than the flat profile expected from an inert body. Engineers checked for instrumental issues, cosmic rays, and background contamination. None were found. The activity was real. This early outgassing suggested the presence of highly volatile ices, such as carbon monoxide or carbon dioxide, and possibly even more exotic compounds capable of sublimating at very low temperatures. It was not only the timing that stood out, but also the consistency. Night after night, the signal remained steady, indicating a process extending deeper than surface frost. Comparisons with ground-based data from ZTF and ATLAS confirmed the behavior. The comet was shedding material far earlier than standard models predict. This early activation set the context for every anomaly that followed. If the object was already volatile at 6.4 astronomical units, what else might be hidden within its composition? Within 2 weeks of the official announcement, observatories worldwide turned their attention to 3I Atlas. The Minor Planet Center logged 122 observations in July alone from 31 different observing sites. Photometry arrived from Chile, spectroscopy from Hawaii, imaging from South Africa, and time series data from Australia. Alerts spread rapidly through professional networks and amateur communities, triggering fast scheduling on instruments ranging from backyard telescopes to major observatories. Acting as the central clearinghouse, the Minor Planet Center in Cambridge standardized and distributed the data. Each new measurement refined the orbit, reduced uncertainties, and clarified the object's trajectory through the solar system. This flood of observations was not merely about tracking a moving point of light. It was an effort to capture every possible detail before the object faded from reach. The sheer scale of the response reflected more than curiosity. It signaled how seriously the scientific community viewed this enigmatic interstellar visitor. It reflected a scientific community moving with urgency, fully aware that an interstellar object of this scale might not pass through our neighborhood again for hundreds of years. Every new observation strengthened the growing body of data, and as the numbers accumulated, so did the inconsistencies. The closer astronomers examined the object, the more unusual features emerged. Conditions were ripe for a debate that would pull in specialists from across planetary science. Dennis Bodewitz at the University of Maryland focused on a basic but critical question: how much material was the object losing as it traveled toward the sun? The answer was startling. At a distance of 2.9 astronomical units, 3I Atlas was releasing water at roughly 40 kilograms per second, comparable to a fire hose blasting at full force, but occurring in deep space where most comets remain frozen and inactive. Photometric mass estimates compiled from dozens of observatories pointed to a scale far beyond anything seen from previous interstellar visitors. Loeb estimated that 3I Atlas was nearly 1,000 times more massive than Oumuamua, the first interstellar object detected in 2017. That difference was not marginal. It was the difference between a city bus and a fully loaded cargo ship. Standard population models suggest that objects of this size should enter the inner solar system less than once every 10,000 years. Yet this one appeared bright, highly active, and shedding water at a rate that surprised even veteran comet researchers. The activity was not a brief flare-up. Observations spanning July through September showed a steady, sustained release. The brightness of the coma tracked closely with the measured water production, confirming that the object's substantial mass was feeding a continuous outflow. This was not a small, dusty ice ball responding weakly to sunlight. It was a massive body carrying enough volatiles to drive strong jets for months on end. Bodewitz and his collaborators traced the water vapor using a combination of ultraviolet and optical observations, cross-checked with both ground-based telescopes and space-based instruments. Each independent data set pointed to the same conclusion. 3I Atlas was operating on a scale that challenged existing expectations for interstellar objects. Its size and sustained activity forced researchers to reconsider what kinds of bodies could be expelled from other star systems and how often encounters like this might actually occur. Then came results from the James Webb Space Telescope that drew immediate attention. Infrared spectra revealed carbon dioxide levels exceeding water by a ratio of roughly 8:1, an almost unheard-of balance in cometary chemistry. In most solar system comets, carbon dioxide rarely rivals water vapor. In this case, water was present, but carbon dioxide dominated, implying formation conditions far colder or more unusual than anything commonly seen nearby. Webb scientists debated possible explanations. Some suggested formation in an environment rich in carbon dioxide. Others pointed to long-term processing by cosmic rays over billions of years. And a few wondered whether an even more unconventional mechanism was involved. No single hypothesis matched the observations perfectly. The team ultimately outlined several possible scenarios without settling on a definitive answer. The anomaly remained unresolved. By chemical standards, the coma of 3I Atlas was extreme. Changes in color added yet another layer of complexity. Throughout July 2025, both ground-based and space-based photometry recorded a consistent shift. The coma, initially relatively neutral in color, grew progressively redder night after night. This was not the slow, gradual reddening typically seen as cometary dust evolves. The transition was sharp, measurable, and independently confirmed by multiple observatories. Spectroscopists interpreted the trend as evidence of surface modification, possibly caused by cosmic radiation exposing deeper, more processed material, or by the release of complex organic compounds as heating increased. Instrumental effects were ruled out. Every dataset confirmed the same reddening trend. Polarimetric measurements from the Very Large Telescope delivered another surprise. Light scattered by the coma showed unusually strong negative polarization, meaning the dust grains interacted with light in a way rarely observed except among distant objects at the edge of the solar system. The values closely resembled those measured for trans-Neptunian objects, bodies that orbit far beyond Neptune. For an interstellar visitor, this was an uncommon and telling signature. The Webb team, already grappling with the carbon dioxide imbalance, now faced dust properties that pointed toward origins in the coldest, darkest regions of a planetary system, or perhaps somewhere even more remote. Any one of these measurements could be explained in isolation. Together, they formed a pattern that standard cometary chemistry struggled to accommodate. The list of anomalies continued to grow, and the object's journey through the solar system promised to raise still more questions. Orbital analysis of 3I Atlas introduced a different kind of surprise, unrelated to composition or outgassing and focused instead on geometry. Its trajectory through the inner solar system was inclined by only about 5 degrees relative to the ecliptic. That is an unusually flat approach, threading between planetary orbits in a way that allowed relatively close passages to Venus, Mars, and Jupiter. For an interstellar object, such alignment is uncommon. Most known interstellar visitors arrive on steeply inclined paths, slicing through the solar plane at sharp angles. By contrast, 3I Atlas followed a route that seemed almost optimized for prolonged exposure, slipping through the planetary region with minimal tilt. Loeb and his collaborators calculated the probability of an interstellar object arriving on such a low-inclination trajectory at roughly 0.005%, about 1 in 20,000. In practical terms, among 20,000 randomly arriving interstellar objects, only one would be expected to follow a path this flat. Loeb cited this improbability as yet another anomaly, suggesting the trajectory might not be entirely random. Others disagreed. Mathematician Hector Sosa Navarro argued that such probability estimates suffer from hindsight bias, calculating odds after observing a rare event. He noted, does not imply the event itself is unnatural. In a universe containing billions of stars and countless wandering objects, rare alignments are inevitable. Even so, the geometry remains striking. A 5-degree inclination combined with a sequence of planetary flybys added another piece to the puzzle. Each individual oddity could be dismissed on its own, but with the trajectory now added to the list, the catalog of outliers felt complete. The real issue was no longer whether any single feature was strange, but how many unusual properties could coexist in one object before coincidence began to resemble a pattern. On October 29, 2025, at perihelion, 3I Atlas swept around the Sun and revealed something impossible to ignore. 7 distinct jets erupted from a nucleus, each a powerful stream of gas and dust blasting outward into space. The longest extended nearly 1.86 million miles, close to 8 times the distance between Earth and the Moon. These were not faint, delicate tails. They were intense, violent outflows, visible even in low-resolution images. The nucleus itself, barely more than a point of light, became the center of a sprawling and dynamic structure. Some jets curved outward in near symmetry, while others formed sharp, angled plumes that shifted from hour to hour as the body rotated. The brightness of these jets far exceeded anything recorded in the previous weeks. Estimates based on pixel intensity suggested a spike in mass loss so extreme that existing models struggled to accommodate it. At peak activity, the object was likely shedding material at rates orders of magnitude higher than the steady outflow measured earlier at 2.9 astronomical units. For a short time, its behavior rivaled the most dramatic cometary outbursts ever observed. No single observatory could claim credit for the discovery. The first images surfaced on amateur astronomy forums, complete with timestamps and location data. and were rapidly verified by observers across the globe. Each new image reinforced the scale of what was unfolding. For amateur astronomers, it was a moment of validation, while major facilities were offline or limited. Backyard telescopes captured the raw physics of an interstellar object at its most extreme. The spectacle was undeniable. Then, as the jets weakened and the object moved away from the sun, a different kind of quiet emerged. It was not the silence of nature, but the silence of unanswered questions. For 43 days, official communication channels offered nothing. During the most chaotic phase of 3I Atlas's passage, when it was at peak activity and closest to the sun, NASA released no public updates. There were no briefings, no confirmations, no rebuttals of what amateur observers were posting online. The absence did not go unnoticed. In that void, speculation surged. Analysts at the University of Washington monitored online activity as interest exploded. Their review found more than 700 social media posts referencing 3I Atlas during the blackout period. Over 280 of those mentioned aliens in some form. Hashtags steadily shifted from astronomy into conspiracy territory, with each new amateur image feeding another wave of viral claims. Reddit discussions and YouTube analyses scrutinized every pixel of the jet images, hunting for hints of structure, machinery, or intent. On X, accounts with large followings posted daily theories about signals, suppression of data, or what authorities were allegedly hiding. The University of Washington team went beyond simple counts. They traced how rumors propagated, showing how a single speculative post could branch into hundreds of derivative narratives, each amplifying uncertainty. Mainstream media largely held back, waiting for official statements, and the rumor ecosystem expanded to fill the gap. By the third week, alien-focused content overwhelmed discussions of chemistry, physics, or orbital mechanics. For many observers, the prolonged silence itself became a form of evidence, with no authoritative answers. The most extreme interpretations flourished. The situation was primed for controversy, awaiting any response from official sources. On November 19, 2025, after 43 days of silence, NASA finally responded. Amit Chatria, the agency's designated spokesperson, delivered a clear and unequivocal message. The object, he stated, is a comet. It looks like a comet, behaves like a comet, and all available evidence supports that conclusion. There was no hedging and no ambiguity. The timing was deliberate. After weeks of unchecked speculation, NASA's statement functioned less as a technical update and more as a reassertion of narrative control. Chatria emphasized that all lines of evidence, from orbital behavior to chemical signatures, aligned with known cometary processes. According to NASA, extraordinary claims circulating online were not supported by data. The statement referenced ongoing observations from Hubble, the James Webb Space Telescope, and multiple ground-based facilities, all reporting consistent results: volatile ices, a dust-rich coma, and jets driven by solar heating. The wording was measured but firm. The object's interstellar origin, unusual chemistry, and dramatic perihelion activity all fell within the known range of comet behavior. The message to the public was clear. The science pointed toward natural explanations, not technology or intent. Still, for many, doubt lingered. Was this confidence fully justified? Or was it an answer designed to restore stability after weeks of uncertainty? The official position was now clear, but the discussion was far from over. Brian Cox described 3I Atlas as a completely natural object composed of carbon dioxide, water ice, and cosmic dust, a characterization consistent with mainstream scientific literature. Peer-reviewed studies addressing its anomalies did so by layering natural explanations rather than invoking extraordinary ones. Jason Wright, a prominent exoplanet researcher, argued that the observed outliers are precisely what one might expect from an interstellar comet formed in another planetary system. In this view, every oddity, nickel without iron, a reddening coma, an extreme carbon dioxide to water ratio, fits within the broad diversity of cosmic chemistry. Yet the details within those same papers reveal unresolved uncertainty. faced with the 8-to-1 carbon dioxide to water ratio. The James Webb team outlined 3 possible explanations: formation in a carbon monoxide-rich environment, prolonged cosmic ray processing, or an as-yet unknown mechanism. None fully accounted for all observations. Rather than choosing one, the team presented all 3 possibilities. Additional complexity came from Roma Mazzoli's analysis of the surface. His work suggested that cosmic rays had altered the outer 50 to 65 feet of material, burying the original chemistry beneath billions of years of radiation damage. He described this as a paradigm shift. What telescopes observe today may not reflect the object's birthplace at all, but a surface profoundly transformed during its long journey through interstellar space. The consensus that emerged was cautious. Astronomers broadly agreed that 3I Atlas is interstellar, extremely old, and the largest object of its kind yet detected. But its chemistry, ratios, and altered surface leave significant questions unanswered. The dominant interpretation remains rooted in natural processes, even as the literature openly acknowledges how much remains unexplained. Avi Loeb responded to the growing list of anomalies by formalizing his skepticism. In July 2025, he published a peer-reviewed paper that went beyond questioning the mainstream view. He introduced a personal framework for assessing the likelihood of a non-natural origin, which he called the Loeb scale. He initially rated 3I Atlas at 4 out of 10. As new data accumulated and anomalies continued to stack up, he raised the score to 6 by autumn. His argument relied heavily on statistics. He calculated that encountering an interstellar object of this mass should occur less than once every 10,000 years. To him, the odds were not merely low, but vanishingly small. He also pointed to the trajectory, estimating only a 0.005% chance that an interstellar object would pass through the inner solar system on such a flat, ecliptic skimming path. In Loeb's view, these were not random quirks, but clues suggesting the object did not follow the standard script for comets or asteroids. The response was swift. Mathematician Hector Sosa Navarro labeled the probability arguments a statistical fallacy, noting that calculating odds after an event has already occurred does not imply anything unnatural. In a galaxy containing billions of stars and immeasurable debris, rare alignments are inevitable if one observes long enough. Even so, the Loeb scale kept the debate alive. With each additional anomaly, the central question grew sharper. How many outliers can accumulate before coincidence demands closer scrutiny? By December 19, 2025, the situation had reached its final phase. The numbers were clear. At roughly 270 million kilometers, 3I Atlas was making its closest approach to Earth. The last opportunity to extract meaningful data before it disappeared into deep space. Observations from ALMA introduced another surprise. Methanol levels in the coma were measured at 4 times those typically seen in comets. Martin Cordiner, one of NASA's leading astrochemists, described the result as difficult to explain without invoking a substantial reservoir of precursor molecules. Methanol plays a central role in the chemical pathways that lead to life's building blocks. This finding joined an already dense stack of unresolved questions. Estimates place the object's age between 7 and 14 billion years. Its origin had been erased by a journey that may have carried it past at least 25 stars. Its future pointed toward permanent escape, accelerating away at more than 150,000 miles per hour. 3 interstellar objects had now been detected in less than a decade, each expanding knowledge while revealing new blind spots. For 3I Atlas, cosmic rays had altered the surface to a depth of about 60 feet, burying any pristine chemistry beyond the reach of current instruments. No one could identify its home star system. There was no way to rewind time and observe its formation. The closest look was happening now. And once this window closed, the trail would go cold forever. Final images, spectra, and measurements would be archived. But the core mysteries, its true composition, its birthplace, and the reasons behind its chemical extremes might never be fully resolved. As the object receded, evidence and uncertainty remained inseparably intertwined in the darkness. At this moment, the most powerful telescopes on Earth and in space were fixed on a messenger billions of years old. The answers hovered just beyond reach, Peer-reviewed anomalies and official assurances stood side by side. Unresolved, the data set was finite. And after December 2025, the opportunity would be gone forever. Science advances through unanswered questions. Whether 3I Atlas proves to be a rare cosmic accident or something more. What matters now is what we demand to understand before it vanishes for good.